In this video, let's look at laws of logarithms. Whether you like it or not, you will see logarithms everywhere in mathematics. Whatever course you take, it doesn't matter what level it is, you will see logarithms everywhere. That's why I suggest you spend time to understand logarithms intimately. What is a logarithm? In simple terms, logarithm is just the inverse operation of exponentiation. Exponentiation is something like 3 squared or 5 squared. So you have a base and an exponent, and you write it this way. That's what we call an exponentiation. Um, there's a connection between logarithms and exponentiation, and you can see it right here. This exponentiation is what we just seen, um, and so there's a base a. There's the result on the right hand side, and then there's the exponent. So when you write a to the x equals b, so that's the exponentiation. Now logarithm uses the same ingredients. It uses a, it uses b, it uses x. But the way it does this is at first, it's not very familiar to most people. You can see now. So the way we read the equation on the right hand side is we say uh, log of b to base a is equals to x. In a way, this logarithm tries to find the exponent x. If you go back to this equation right here, what the log does is it asks the question, what exponent of a produces b? I'll say that again. What exponent of a produces b? It turns out it's x. So coming from here will help you logarithms on the right hand side. In mathematics, when you have double arrow like this, these are called implication. The way you read it, you say a to the x is equals to b if and only if the logarithm of b to base a is equals to x. So which means there's a forward arrow, which means this equation here implies the equation on the right hand side. Similarly, the equation on the right hand side implies, using the backward arrows, the equation on the left hand side. Okay? There are some things you need to know. So a and b have to be positive numbers. They have to be positive real numbers. And also a cannot equals 1 for obvious reason, because if a is equals 1, it doesn't matter what x is here. X can be anything. For example, 1 raised to 1 will give you 1. 1 raised to 100 will give you 1. 1 raised to 1 million will give you 1. Okay? So in that case, so that's undefined. And you will see that that's the same thing with logarithm. So we cannot have a equals 1. Okay? Of course, x here can take any real number. It ranges from minus infinity to plus infinity. All the numbers you can think of on the number line, so x can take on those values. Okay? So that's the dynamic. You will understand as we go along in here. But let me just show you a few examples. Now, we say the log of 8 to base 2 is 3, since 2 cubed equals 8. So this is asking the question. Remember when I said, what log of base a produces b? It's x. And at the same time, look at the exponent, right? What log of a, sorry, what exponent of a produces b? Is x. So that's the same thing that we're trying to answer here. So here we're saying, what exponent of 2 produces 8? It turns out it's 3, because 2 cubed equals 8. So we need to exponentiate 2 to 3 to produce 8. Another example, log of 1000 to base 10 equals 3, since 10 cubed equals 1000. So we're answering the question, what exponent of 10 produces 1000? What exponent of 10 produces 1000? It turns out it's 3, because 10 cubed gives you 1000. Okay? So I hope that's a little bit clearer. Now let's look at some of the rules when dealing with logarithms. And the very first one is logarithm of 1. We say logarithm of 1 to base a equals 0. And that's because a raised to 0 equals 1. Now you see the connection between exponentiation and logarithm. Okay? Now it doesn't matter what a is. It doesn't matter what a is. As long as the exponent is 0 equals 1. Of course, we don't want a equals 0, because a 0 raised to 0 is undefined. But any number, we don't care what it is. In fact, even negative exponent, even negative basis, you can even have minus 1 raised to 0. That will give you 1. Okay, so here are some examples. We have log of 1 to base 7 is 0. Why? Because 7 raised to 0 equals 1. So asking the question, what exponent of 7 produces 1? It is 7 raised to 0. What exponent of 2 produces 1? It's 0. Because 2 raised to 0 equals 1. What exponent of pi produces 1? It is pi raised to 0. Okay? So I hope that makes it clear. So that's the logarithm of 1. Change of base. Okay. Now we talk about the base a here. So one thing I like about logarithms is that it's actually very flexible dealing with bases. You can change bases anytime, depending on the problem you're solving. Okay. So here I have log of b to base a. So I can write it as a fraction this way. It's going to be log of b to base c divided by log of a to base c. You can see now this b goes on top, this a goes in the denominator. And then I invented a new base c. This c could be anything. It could be 1000, it could be 10, it could be 2. Okay? And then you can also completely drop the c and just write it as log b over log a. So that's perfectly acceptable. This is actually going to be useful when you're trying to compute stuff using your calculator. Okay? Writing it this way, because most calculators are not built to handle this one. Most calculators are built to handle logarithm to base 10 only. Okay, so that's why this change of base is very important. Okay, so yeah, you can rewrite logarithm in terms of a different base of your choice. Okay, we have an example here. What is the log of 10 to base 2? So using the change of basis here, you can write as log of 10 to base 10 divided by log of 2 to base 10. Now log of 10 to base 2. So yeah, so now log of 10 to base 2, this one now you can feed this into your calculator. In fact, let me see if I can bring up the calculator. Yeah, just to see the approximate answer here. So log of 10 divided by log of 2. This is going to be an approximation. So you can see it's 3.32. approximately 3.32. Okay, yeah, 3.32. Now, yeah, so this is what I just did. So log of 10 to base 10 is equals to 1. And you can see that if you do a change of bases like this, you can also do another change of bases here. It's going to be log of 10 divided by log of 10, so it's going to equals 1. Now log of 2 to base 10 is approximately 0.301. And then now uh, computing this one now is just a matter of dividing 1 divided by 0.301. So it's going to be 1 divided by this is 3.32, which I just showed you right here. Okay. So in fact, you can compute log of 10. Let me backspace first. Log of 10. So that should give you 1. Right? It's 1. Because you are asking the question, what exponent, this is to base 10. So most calculators are equipped to base 10. So you're asking the question, what what exponent of 10 produces 10? So it's 1. So 10 raised to 1 equals 10. So if you come from that angle, you will have no trouble with logarithms, okay? So and then the next one we have, let me backspace here. We have log of 0. Sorry, log of 2. So 0.301, which is this one right here. Okay? And then now we're asking the question. So now just forget about all these values. Just ask yourself, what is the base? Because remember, this is the goal. Log of 2 to base 10. You ask them the question, what is the exponent? So log of 10 to, yeah, so anyway, yeah, so that's how you deal with that. And I'll leave it there. Just I don't want to confuse you more. Okay. Okay, next one we have the logarithm of the base. So when the logarithm and the base match like this, log of a to base a, so this is equals to 1, and you can see that easily by looking at the exponentiation. A raised to 1 equals 1. You ask them the question, what is the exponent of a that produces 1? That produces a. What exponent of a produces a? It will be a raised to 1. So let's look at some examples. What is the log of 5 to base 5? That's equals 1, since 5 raised to 1 equals 5. You are asking the question, what exponent of 5 produces 5? Is 5 raised to 1. Log of 10 to base 10. We just saw this in the just a moment ago. Log of 10 to base 10 equals 1. That is because 10 raised to 1 equals 10. Similarly, log of pi to base pi equals 1. So as long as the base and the log itself match, so that's going to be 1. And you can use exponentiation to see why that is the case. Okay, next one we have power rule. This one is very useful. It's very useful rule. We have log of x raised to n to base a. You can write it as n times. So the dot here is a multiplication, a shorthand for multiplication. So n times log of x to base a. So essentially, if you are taking the logarithm of a very big number, if you can write it as a number with some exponent, you can drop the exponent and then just take the log of the base or whatever the number is. And then once you get the log of that number, you can multiply it by the exponent. This is what it's trying to explain here. Okay, so the logarithm of power is the exponent multiplied by the logarithm of the base. Let's look at some examples. Okay, so log of 25 cubed to base 5. So this is equals to 3. So you can see now I bring the 3 down, okay? And now I can just take the log of 25. So 25, it turns out the log of 25 is, you can also write 25 as 5 squared. So there's another 2 that I can drop again. That's why I have a 2 here. This 3 here is the one from here. So the 5, I write as 5 squared. So that's that 2, you can see here. I can also drop it again. So it's now become 3 times 2 equals 6. And then now, what is left over now is you have 3 times 2 times log of 5 to base 5. And we saw previously that when the base and the logarithm match, that will be equals 1. So this whole thing become 1. Okay, so that's why the log is now 6. 3 times 2 is 6. Okay, the product rule. This is also another useful one. This one says when you have a factors of numbers x and y, and you're trying to take the log of x and y to base a, you can just take the log of each factor individually to base a, and then just add them up. How convenient is that? It's super convenient. It's not easy to see right now, but when you're dealing with really large numbers, this will save you time and even computing time when you're dealing with computers. Okay, so the logarithm of a product is the sum of logarithms of its factors. Okay, so let's see some examples. Log of 8 times 4 to base 2. So you can see now this number here, 8 times 4 is the same as 32. 8 times 4 is 32. So log of 32 to base 2, I can write it as log of 8 to base 2 plus log of 4 to base 2. Always keep in mind that you always carry around the same base. You cannot change these bases here. And that's true also for the previous rules we just saw. Now you can see this is true because now 8 I can write it as 2 cubed. 8 become 2 cubed, right? Now 2 cubed using the power rule that we just saw earlier. So the 3 can drop to the back here. So now you're taking log of 2 to base 2. Log of 2 to base 2. So that become 1. So for this term you get 3 here. That's why I have a 3 here. Now the next term, log of 4 to base 2. Log of 4 to base 2. I can write 4 as 2 squared. So I can drop the 2 to the back here. So it becomes 2 times log of 2 to base 2. And log of 2 to base 2 is 1. So that's why this term now is 2 here. So 3 plus 2 is 5. Now if you only focus on the right hand side, 8 times 4 is 32. So, and 32 is the same as 2 raised to 5. So this whole thing here, 8 times 4, you can replace it with 2 raised to 5. And then of course you can drop the 5 to the back here. So you only have 5 times log of 2 to base 2. So log of 2 to base 2, that becomes 1 because the base and the log match. And so yeah, so that's the product rule. Just remember, use this rule correctly, because I've seen students, sometimes they change the base, and just keep in mind that the base has has to match. And this is also true for power rule and stuff like that. Okay, the quotient rule. The quotient rule, this is super useful. Log of x over y to base a, you can write it as log of x to base a minus log of y to base a. Again, you can see the bases here have to be consistent. A everywhere. Okay? And now this is super convenient because I can just take the log of x to base a, log of y to base a, and then subtract the two numbers. That's super convenient. Okay? So this is saying that the log of a quotient is the difference of the logarithm of the numerator and the denominator. So when you have a fraction, the top number is called a numerator. The number y is called a denominator. Okay. Let's look at some examples. I have log of 27 to base log of 27 over 9 to base 3. I can write it as log of 27 to base 3 minus log of 9 to base 3. So now I took 27. 27 here is what I have here. This 9 is what I have here. And see also the bases. They have to match. 3, 3, 3 everywhere. Okay. Now, so LHS here is just a shorthand for the left-hand side. If you only focus on computing this left-hand side here, you can do it this way. So the left-hand side is equals to log of 27 over 9 to base 3. And then I can just simplify this fraction here. So 27 divided by 9 is 3. And you can see that the base and the log match. So log of 3 to base 3 equals 1. Or I'm asking the question, what exponent of this 3 produces this 3? It is 3. It is 1, because 3 raised to 1 equals 3. Okay. Now we go on to the right-hand side. So you can see the left-hand side is 1. If we produce right-hand side equals 1, then we know that this equation is essentially correct. Okay. So that's the thinking here. So the right-hand side is made of this term minus this term. That's what I have here. Log of 27 to base 3 minus log of 9 to base 3. And you can write 27 as 3 cubed. Okay? 3 cubed to base 3. You can write 9 as 3 squared. So this becomes log of 3 squared to base 3. And then using the power rule that we saw earlier, you can drop this exponent to the back. So this exponent. So you see this 3 goes here. So now you have log of 3 to base 3 and then multiply by 3. Minus, now this 2 can come to the back here. So you have 2 times log of 3 to base 3. And you see the base and the log match here. So this is 1. The log and the base match here. So this is 1. So basically you have 3 minus 2, which is equals to 1. And clearly this shows that the left hand side is equal to the right hand side. So which means this equation here is essentially correct. Okay, so the very last one that I want to talk about is called the inverse property of logarithms and exponents. Okay. So this one says if you have a base b and then you exponentiate it to log of some number k to base b, you get back k. How beautiful is that? When you have this messy left-hand side here produces k like this. B raised to log of k to base b equals k. So this one, it just shows the inverse relationship between log and exponents. And it's saying that if you raise the base b to the log of k with base b, you get back k. As long as these bases match, so this base and this base, they match, you get back k. This is an example of how exponentiation and logarithm undo each other. Okay, because this b here, you see the exponent, that's exponentiation, but in the exponentiation there's also log. So you have exponentiation and log in the same equation. They undo each other. Okay. So I hope that is clear, because this is going to be super useful when you're trying to solve equation, you're trying to cancel things. You can change a number to this form, and then it will be easy to deal with certain factors and simplify things quite easily. Okay, let's go through some examples. So we say 10 raised to the log of 100 to base 10 equals 100. Why is that the case? That is the case because I can write, in fact, I can write the exponent this way. You see the exponent? Just forget about the base 10 here, this 10 right here for now. Just focus on the exponent here. So the exponent, I can use the change of bases that we just saw earlier. So the change of bases, I can write it as log of 100 divided by log of 10. Okay? Like that. And then I can write 100 as 10 squared. Why? Because I want to use the power rule. Now I can drop this 2 to the back. Okay? So the 2 will go to the back here, and you have log of 10 divided by log of 10. And log of 10 and log of 10, this is the same thing. So I can cancel those. Once I cancel those, what do I have? What is left over is 10 squared. And what is 10 squared? It's 100. So 10 squared is 100. That's why 10 raised to the log of 100 to base 10 equals 100. And the trick is because this base and this base here are the same. This base and this base are the same. So this base here is the base of exponentiation. This base here is the base of taking log. That's how you see it. That's how you should see it. I'll repeat that again. This base here is the base of exponentiation. This base here is the base of taking log. As long as those two match, you get back your argument here, the one in the bracket, always. Okay, let's go another step further. Let's see another example. Now, suppose we have the base b equals e. Now, you will see e. So the value of e is 2.7. This is an irrational number. It goes on forever. It is a recurring decimal. It doesn't stop. You will see it a lot in mathematics, engineering, physics. So if you take calculus, you see this base e a lot. Okay. Now, if the base is equal to e, then in the previous equation, I can replace all the bases. Remember, we had b log of k to base b, right? So I replace all the b's with e. So I get e raised to log of e to base k. And that becomes e ln of k equals k. Why? So there's a term called natural logarithm. And that is when you take the special case of base b equals e. You can see right here. Log to base e become ln ln k. So this is called natural logarithm. And this is what most people are familiar with. If you took some calculus classes before, you've seen this before. You know that e ln of anything will give you that anything, right? And it comes from, this inverse property of log and exponent. And here, you can see it where it came from. Okay, I hope that is clear. Okay. Before we so this is the summary of all the rules we've seen so far. We've seen that the log of 1 to base a equals 0, because we're trying to ask the question, what exponent of a produces 1? And that's 0. When the log and the base match, you get 1. Okay, so that's the logarithm of the base. The change of base, you can write log b to base a as a fraction this way. You can invent your own base, or you can even drop the base completely. And then the exponentiation, so the power rule. So the power rule, you can drop the power like this, and it becomes a multiplier. Okay. So the product rule, if you have a number that has the factors x and y, you can just take the log of each factor separately and then just add them up. Or if you have a quotient, you can just subtract the logs of the quotients like this. And then, of course, the special property where logs and exponentiation undo each other. So that's the case there. So this table should give you everything you need so far to understand log. So if you can, I'm not saying you memorize, but if you understand this table and you know how to use them, you should have no problem dealing with logs. Okay, so let's go back to the first equation I showed you earlier. This is more for, like, math students who want to go major in mathematics and you want to know where stuff. For those of you who just interested in knowing the rules, you can ignore this part of the video. But for those who want to go on and study mathematics, let's look at this more like more in depth. Okay. So I claim that a to the x equals b if and only if log of b to base a equals x. So I claim that we can derive these equations. Okay. Now, if we start with the equation on the left-hand side, a to the x equals b, we can show that a to the x equals b implies that log of b to base a equals x. And this is just doing it algebraically. You can argue algebraically. So that's what I will do here. Now, if we take log on both sides, remember I'm starting from here. I'm starting from the left-hand side, and the goal is to end up with the right-hand side. Okay? So if I take the log on both sides of this, what do I end up with? Yeah, it's just log of a to the x equals log of b. Very straightforward, right? In this case here, I'm not even worrying about the base. It could be base 10, it could be base e, it could be whatever. So I'm just taking logs right now, okay? So I omit the bases here, and this is standard in mathematics. You will see that when there's no ambiguity, you can drop the base. But I can also include the base, like base 10, base 2, base whatever you want, okay? So next, I can use the power rule. Remember, this one is an exponent, right? I can take it to the back using the power rule. Remember the power rule, we just saw the power rule. When I have log of x to the n to base a, I can drop the n this way. So it becomes a multiplicative factor, okay? So I didn't do anything fancy there, so just dropping the exponent x. And then, of course, now I divide both sides by log of a. If I divide the left-hand side by log of a, I only have x left over. The right-hand side now, I have log of b divided by log of a. Okay, so that's some progress. And now look, I can rewrite this part of the equation using the change of base formula. Remember the change of base from the table. Log of b to base a is the same as log of b divided by log of a. And can you recognize this equation right here in the box? It's exactly the same as what we have here. So what we have shown so far is that we started with here and we proved, or we showed, the forward arrow. So this is saying that a to the x equals b implies that log of b to base a equals x. So that's good. Next, I would like to look at the other direction. Okay, now let's look at the other direction. Remember, I copied the equation here for your reference so that you can see it. Now I would like to start here. I would like to start on the equation on the right hand side. The goal is to end up with the left hand side. Okay. Now uh, log of b to base a equals x, which is this one right here. You see that I can use the change of base formula that we saw in the previous case. Log of b to base a I can write as a fraction as log of b divided by log of a equals x. I did not do anything. I'm just rewriting the left hand side here. Okay, this left hand side, I'm just rewriting that. I did not do anything fancy. And then now I can multiply each side by log of a. The goal is to cancel log of a. Okay, the goal is to cancel log of a. So if I multiply the left hand side by log of a, so log of a and log of a will cancel. So on the left hand side, I'm left over with just log of b. Now if I multiply the right hand side by log of a, I get x times log of a. And now so this is progress. Now I can use the power rule. So this exponent, I can take it and make it the exponent of a to the x of a, right? It becomes log of a raised to x. So you can go back and forth. You can drop the x, or you can bring back the x here. So that's what I did. And look at this equation right here. It's saying that log of b equals log of a to the x. This can only be true. This can only be true if the arguments are the same. When you have the log of two numbers being the same, the two numbers have to be the same. The two numbers have to be the same. So therefore, we can make the leap and say that b equals a to the x. Okay, which is what we have right here. So what we have shown so far is if you have the equation log of b to base a equals x, it also implies that a to the x equals b. So we've shown the other direction as well. Okay. Yeah. So thank you for watching.